Hello, ladies and gents. We've been talking about the pH scale, and we've been talking about the fact that this is a logarithmic scale. So what that means is one number difference in pH makes something 10 times more acidic or 10 times more basic. And I think this chart is kind of handy to take a look at. So if you go from a neutral pH of 7 up to a pH of 6, it's 10 times more acidic. From 7 up to 5, 100 times more acidic. 7 up to 4, 1,000 times more acidic. But remember, pH is parts hydronium, at least that's how I remember it. So it also is an indicator of hydronium ion concentration. So this is how many hydronium ions are going to be in 1 liter of solution. If you go to a basic pH, these higher numbers are a basic pH. You go from a 7 to an 8, it's going to be 1/10 the number of hydroniums. If you go from a 7 to a 9, 1/100th the number of hydroniums. 7 to a 10, 1/1000th the number of hydroniums. So the larger number equals a small hydronium ion concentration, and this actually gets lower. And as you go to higher pH, the hydronium ion concentration goes up. And as you go to lower numbers, the hydronium ion concentration gets smaller and smaller and smaller, because that's what pH tells us. So let's see if we can kind of do some quick and dirty math using this. How many times more acidic is a stomach acid with a pH of 1 compared to wine with a pH of 4? So we're comparing something, a pH of 1 to a pH of 4. So that's going to be 1, 2, 3. So 1, 2, 3 zeros, 3 powers of 10 times 100. So 1,000 times, with a 1 in front. So 1,000 times more acidic is going to be the stomach acid with a pH of 1 compared to wine with a pH of 4. How many times more basic is ammonia with a pH of 11 compared to baking soda with a pH of 10? So if we're comparing an 11 to a 10, that's a jump of 1. So a jump of 1 is 1 0 with a 1 in front of it. So 10 times more basic going from baking soda up to ammonia. And that is a big jump, 10 times more. You give me 10 times more in my paycheck, I'd be happy. And you probably would be too. So let's look at a real world example of this. Let's say a parent is concerned about should they give their child apple juice with a pH of 3, or should they give their child tomato juice with a pH of 4? So which one is more acidic? Well, as you go in this direction on the pH scale, things get more acidic. So which one is more acidic? Well, actually, it's apple juice. You don't see a lot of parents running around giving their babies tomato juice, but apple juice is actually 10 times more acidic than tomato juice. Interesting stuff once you actually know a little bit of chemistry. All right, hit pause, try these, then we'll go through them. All right, let's go through. So you've got 2 solutions, one with a pH of 5 and 2. So 5 up to 2 is 5 minus 2, that's 3 jumps, so 1, 2, 3 zeros. It's 1,000 times more acidic at the 2 than the 5. You've got 2 solutions, one's a 12, one's an 8. 12 minus 8, that's 4 jumps, that's 4 zeros. 1, 2, 3, 4. Put a 1 in front of it. That's 10,000 times more basic. Now, pH talks about hydronium ion concentration. So we've got a 9 and a 6. Which one contains more hydroniums? The pH of 6 contains more hydroniums. How many times more hydroniums? Well, 9 minus 6 is 3. So 1, 2, 3 zeros, put a 1 in front of it. 1,000 times more hydroniums at the pH of 6 than the pH of 9. Let's go in the other direction. Let's say apple juice has a pH of 3. What's the hydronium ion concentration? Now, this is the quick and dirty method. Remember, we're going to do real math next week. But quick and dirty method says use that pH as the power of 10 number for this. So the concentration is 1 times 10 to the negative 3 moles of hydronium ions per 1 liter of solution. So if that's the pH, that's the concentration of the solution. If we have a soap solution that has a pH of 9, what's the hydronium concentration? Well, the same thing. Quick and dirty, we can use that pH to go to concentration. 1 times 10 to the negative 9 hydronium ions per mole, moles of hydroniums per 1 liter of solution. So how many times more acidic or basic is something with the soap solution with a pH of 9, baking soda with a pH of 8? The soap is going to actually be 10 times more basic than the baking soda at an 8. And that is that difference in pH. Remember, a change of 1 in pH means 10 times more acidic or basic. Now, if you're dealing with a strong acid, and we talked about our strong acids, hydrochloric, sulfuric, and nitric. Sulfuric, remember, is battery acid, nitric acid, and hydrochloric. They're going to have a pH of 0. So what does that mean? Well, their concentration is 1 times 10 to the 0. That's where that pH goes, is right there. Moles of hydronium ions per liter of solution. So what does that tell us? That tells us that the acids are going to completely dissociate into ions. Because remember, water will dissociate into hydroniums and hydroxides into solution, and it's a dance back and forth. But in a strong acid or a strong base, it's all going to go in one direction. There's none of this dancing back and forth, switching partners back to the reactant. It is fully going to go towards the product side, and it's going to fully change into ions. That's what makes a strong acid a strong acid. Now, one of the things that happens is in a solution of acids and bases, you have both, and that's why they come together. It's always referred to as acid-base chemistry. It is the yin and the yang. It is the right and the left, the up and the down. They always come together. And so if you have one, you are going to have the other. In a neutral water solution, it has a pH of 7. And that means you've got some hydroniums and some hydroxides. But as a solution gets more acidic, the hydronium ion concentration goes up. As the solution becomes more basic, the hydroxide ion solution goes up. And so these two numbers kind of swing back and forth between them as something becomes more basic or more acidic. But kind of a nifty piece of underlying mathematics. If you ignore the negative sign, the sum of the powers add up to 14. Let me show you what I mean. So if we look at this, if we have 1 liter of pure water, it's going to contain 1 times 10 to the negative 7 moles of hydroniums and 1 times 10 to the negative 7 moles of hydroxides. If you add the 7 and the 7, 14. If I have coffee with a pH of 5, the hydroniums give us the pH, so that's that power of 10. But the powers are going to add up to 14. So if I want to know how many hydroxide ions I have, this is going to add up to 14. 5 plus 9 is 14. I will know, if I know the hydronium ion concentration, I can figure out the hydroxide ion concentration. The same is true for basic solutions. pH of 8 for baking soda means that I have a concentration of 1 times 10 to the negative 8th hydroniums. The sum has to be 14, so my hydroxide is going to be 1 times 10 to the negative 6. And you always have to stop and think about this because this gets a little weird. Remember, this is the larger number. It is a base, and because it's a base, it has more hydroxides than hydroniums. I know, negative exponents can hurt your brain. So for low pH, they have more hydroniums. So for our acids, they're going to have big hydronium numbers. These numbers are going to be bigger. For our bases, going this direction, the hydroxide ion concentration is going to be bigger. This number is going to get bigger. I'm going to go back to my red pen because I'm trying to keep consistent with my colors here. Whoops, woo, this is going to get bigger. And if you look at both of these, acids mean you have lots of hydroniums. Bases mean you are going to have lots of hydroxides. And the sum of the powers are going to be 14. All right. If you have a strong base like lye, a very strong base like lye, the pH is going to be 14. So what that means, because remember, pH is based on hydroniums. So that means the hydronium ion concentration is 1 times 10 to the negative 14 hydroniums. Well, the sum of the two, hydroniums and hydroxides, are going to equal 14. So if the sum of the two equal 14, what's my hydroxide concentration? 1 times 10 to the 0. And that's going to be my hydroxide ion concentration. You just have to look at the two pHs. They're going to add up to 14. Try this one. Hit pause. Try this. Okay, let's take a look. If it's a pH of 12, remember pH is based on hydronium, then the hydronium concentration is 1 times 10 to the negative 12 hydroniums per liter. So what's the hydroxide? The powers have to add up to 12. That's going to be 1 times 10 to the negative 2 hydroniums per liter. Pretty easy. You just have to be able to add things up to 12 to be able to figure out how many hydroxides and how many hydroniums. I know, hydroniums, hydroxides, easy slip of the tongue. All right, hit pause, try this one. Okay, pH is based on hydronium, so this is going to be 1 times 10 to the negative 10 hydroniums per liter. And so hydroxides, 1 times 10 to the negative 4 hydroxides per liter. Getting it? Yeah, see, it's not too bad. Not too bad at all. Very last idea I'm going to mention is this for this chapter. Sometimes you are going to see a chart that's going to look like this, and it's going to contain POH. Well, what is POH? POH is potential hydroxide. Potential hydroxide is, instead of talking about the potential hydrogen, it's the potential hydroxide. Just wanted to mention it because you will see it on assorted charts and graphs, and I wanted to explain what is that. It is basing the concentration on those hydroxide ions, those OH negatives, instead of basing it on the hydronium ions. Chemists look at a variety of different things, and you will see that once in a while, so I wanted it not to be a surprise. Okay, folks, talk to you later. Bye-bye.